No, sniper. I am the teacher.
So for the ones who are coming in right now, I just want to let you know that I am recording the sessions to put on Blackboard later. I just don't want anyone to know that your voice is being recorded without being told first. Obviously, the camera's not going to be on you; it's going to be on me. But so in regards to homework 6, I'm going to do one problem first, and then I'll try to get to it.
The problem you're doing from the new stuff, doing the second law or whatever?
Yeah.
Okay.
Yeah.
The second problem,
What about?
or for homework 6, is it the second problem?
I'm doing an example from the suggested additional topics
Okay.
because I believe Dr. Deal mentioned that you might get extra credit for doing those ones.
Okay.
Did he mention that to anyone?
No. But
Oh, no, okay. Well, that might just be in my imagination, but the suggested problems are harder than the homework problems. So I'm gonna do the harder problems so that the easier problems should come quicker.
all right.
Okay, so the question asks you, boxes A and B are on a conveyor belt that is initially at rest, and then the belt is suddenly started in the upward direction. So that slipping occurs between the surfaces. If the coefficients of friction are, this is the one for A, and this is the coefficient of kinetic friction for B, the question asks you to find the acceleration of both boxes. So, does anyone have an idea of where we should start? And to give a hint, the last thing that I just drew is a good place to start. It has something to do with the coordinate system.
Coordinate transformation.
Yes. So you don't necessarily need to do the coordinate transformation, but it will make your life easier. So I'm going to define a new coordinate system based on this system right here. We see that the whole system itself is tilted 15 degrees up. So it's a good, it'd be a good idea to perhaps shift the coordinate system in a manner like this instead. So if I'm using a coordinate system that is now defined by the problem, this is what it would look like, where I'm defining that EX, the EX direction, is going up this way, and then the EY direction is now normal to the surface, like that. So directly from the problem, we can get that this angle right here is 15 degrees. Everyone with me? 15 degrees. So then that means that this angle right here, the angle between EY unit vector and the J unit vector, is also 15 degrees, which I will refer to as theta in when I don't want to use the number itself. So, coordinate transformation. Okay. So in the EX direction, what is the I component? So we're looking at this unit vector right here, and I'm trying to figure out what is the I component of it. So if theta is right here, then this unit vector has an I component of cosine of theta. Doing the exact same thing, I'm looking for the J component of this unit vector EX, which is going to be sine of theta this time. So that's the EX coordinate transformation done. So we do the EY coordinate transformation in the exact same manner. So if I'm looking for the I components of this vector, it's definitely negative because I'm saying that the I component is this way. So we can see that EY is definitely negative. And it is going to be sine, because if theta is right here, the opposite is this thing right here. So sine of theta. Then finally, I am looking at EY and the J component, which is going to be cosine, and it's positive. Okay. So now we know how to define our system in terms of our new unit vectors, EX, EY. So the next step we should do is well, what do you guys think? What do you think we should do now that we have the coordinate transformation done? Any ideas? So does kinetic diagram and free body diagram ring a bell to anyone? Definitely free body diagram should. So I am going, because these are two unique things, box A and box B, I'm going to start with a free body diagram of just box A. So drawing this again. So in statics, when you did the sum of the forces and the sum of the moments, they were always 0. So when you drew your free body diagram, you didn't need to really relate that to anything else because what it was related to was just 0. So this is dynamics, things are moving. So we have, this is the free body diagram, and the free body diagram is equal to the kinetic diagram. So this should tell you the sum of the forces is equal to mass times acceleration, whereas in statics, the acceleration was 0. So that's why you didn't really need to do this. You didn't really need to relate a free body diagram to anything other than itself. So I'm going to put the forces that I know are acting on this system, at least on block A. So one obvious one is weight. So I'm going to call that WA. And remember, I'm using this coordinate system. So one force obviously acting on this is the weight of A. So can anyone tell me one more?
Kinetic friction in the EX direction.
Yes. Yes, you are right. Which way do you think the friction goes?
Is it going up? Well, is the block going up and to the right, or is it?
Yes, the block is going up and to the right.
So it'd be in the opposite direction, going down to the left.
So when I actually was doing this problem first, I actually did think that, but there's something in the problem that tells you that, like, eventually that's going to happen, yes. But at this instance, it tells you slipping occurs, which means that although the conveyor belt is going to move that way, and eventually the boxes are too. Slipping means that the boxes are going to initially slide down a little bit.
Okay.
So if the boxes are initially going down like this, they like momentarily the friction is going to be going up that way.
Okay.
So that one will get you off guard. So, okay. Then there is one more force here. So we have the weight of A, the frictional force on A, and then the normal force of A, which I'm going to call NA. Okay, so that's all the forces. And there's one more thing that we're assuming. We're assuming that block B right here is moving faster, just slightly, than block A, so that block B is not touching block A. So that's important because if they were touching, there would be a normal force of A exerting on B, and vice versa, B would be exerting a normal force on A. But I'm telling you, it's okay to assume that this block right here, B, is going to be just slightly ahead of block A. So there's a gap between them. They're not touching. So this is all the forces that we have to worry about. And then, so the sum of the forces equals mass times acceleration. So this is the mass of block A times the acceleration of block A, specifically in the EX direction. And then similarly, we have the mass of block A times the acceleration of block A in the EY direction. Okay. So I'm going to look in the EX direction first, the sum of the forces in this direction. So we have the frictional force of A plus there is a force due to the weight of A, but it's a little more complicated, and I'm going to derive it for us. And then this equals mass of A times the acceleration of A, specifically in the EX direction. So because of our new coordinate system, the weight of A has components in both the EX and the EY direction, whereas conventionally, forces due to gravity would only act in the J direction. But because we did a coordinate transformation, the weight of A is going to have components in both of these coordinate systems, both of these unit vectors, rather. So, and this comes up all the time. So I'm going to derive how you figure out what the weight of A should be in EX direction. So as you can see here, I have the I unit vector and the J unit vector, where those are always constant for no matter what problem. And then our new coordinate system, which we know that theta is this angle, and we know that theta is also this angle. So we know that the weight of A always is in the negative J direction. And from this, I can directly define that this angle right here is theta, because this one was too. So that's just a geometric relationship that you can define. So that is theta. So looking at this now, this arrow right here, this is negative EX direction, and this is negative EY. So I can see that the weight of A is acting in both negative EX and negative EY. So then I need to define I need to use trigonometry to find out what the components are. So specifically in EX direction, we have, it is negative sine. Negative sine of theta. So that's for EX. Okay, so I'm going to call this equation 1. So going back into equation 1, have the frictional force of A, which is now then minus WA sine theta equals mass of A times acceleration of A in the EX direction. And remember, we have the weight of A, so the mass of A mass of A is the weight of A divided by gravity. So although we don't have it directly, it's a simple computation to get it. So looking at this, we have the mass of A. We do not have the acceleration of A, but that's the entire point of the problem. So it's okay not to know that. What's up?
The acceleration of A, is that a subscript below that for the EX, or is that also part of the equation?
This is, it's a subscript.
Okay.
We know the weight of A, we know sine of theta, that's just a computation, but we do not know the frictional force acting on A. So, friction by definition is, it's the coefficient of friction times normal force, right? So for our problem, this means the frictional force of A is equal to the kinetic coefficient of friction, which is given, times the normal force of A. So looking at this equation now, we have this. We don't know the frictional force of A, but that's okay because that's what we're trying to solve for right now. However, we also do not know the normal force of A. So I found out everything I can about summing the forces in the EX direction. I need to now look in the EY direction. So, this is where we left off. And the reason why I'm now going to sum the forces in the EY direction is because I found out all the information I can from the EX direction. So now in the EY direction, we have so if our new coordinate system looks like this, and we know the boxes are going to move in this direction, directly along the EX unit vector, there is thus no acceleration in the EY direction. There's acceleration in the J, but not in EY. So we can say the sum of the forces in the EY direction equals 0, which is very helpful. Okay. So, I'm going to use this again, this free body diagram again. And I know this component is 0. So then I have the normal force of A, which is acting directly in the EY direction. It has no component in EX. And that minus the weight of A, and it's the weight of A when we were summing in the EX direction was sine, so it's definitely going to be cosine here. Cosine of theta equals 0. So the normal force of A equals the weight of A times the cosine of theta. Okay, so that's what I was trying to find all the way over here when I got stuck with the frictional force of A, because I had everything except the normal force of A. So now the frictional force of A is equal to the given coefficient times weight of A cosine theta. Weight of A times cosine of theta. Okay. So Are you guys good if I erase like the problem statement? Everyone cool? So that equation that I labeled 1 before, I'm going to look back at it now, and I have a lot more information. So I have the frictional force of A I just defined as this right here, times W, the weight of A, times cosine of theta. And then we know that the next part of that is weight of A times the sine of theta. And this equals the mass of A, which is also equal to the weight of A divided by gravity times the acceleration of A. And recall, this is still just in the EX direction. So now, last step is plug and solve. So this last part is just putting in the numbers. So 0.3 was given. The weight of A was given as 100 pounds. Cosine of theta, where theta was given as 15, minus 100 times the sine of theta. Then we're working in English units, pounds, so gravity is 32.2 feet per second squared. Feet per second squared divided by the weight of A, which is given as 100 pounds. All of this equals the acceleration of A. So one thing I think you should do on tests is always check your units. I know it's just like a very long thing to keep track of, but like for instance here I have pounds minus pounds, so the result is still pounds, and then that is multiplied by an acceleration term divided by pounds. So the pounds is going to cancel out. So what my equation is saying is that acceleration equals acceleration. Yes, of course it does. So when you put all this in your calculator, the answer is 0.997 feet per second squared. That's the acceleration of A. Is there any questions?
Is that the total magnitude of the acceleration of A, or is that just the acceleration in the EX direction?
You're right, I should have said that. Acceleration in EX. Acceleration in the EX direction. So you could say that one of two ways. So you could say it's the acceleration in the EX direction, or you could say like this too, 15 degrees, like the angle 15 degrees, because we know the system's slanted 15 degrees. So these problems take a long time. So the question also asks the acceleration of B. So I'm going to do the whole thing again. Is everyone good if I erase everything?
Mm-hmm.
Yeah, okay. Or I'll keep the coordinate transformation, but. Okay, so now block B. I am just going to change the subscripts. Okay, so now I'm working on block B, and the free body diagram and the kinetic diagram are going to stay exactly the same. It's just the subscripts that changed. That's good with everyone? Yes. Okay. So. Next step. The sum of the forces in the EX direction. So we have FB in the positive EX direction as we defined up here, minus WB, but it has components in both directions. So I'm going to derive that again, is equal to the mass of B times the acceleration of B in the EX direction. So, same way as we did before, the weight of B has components in both. So, it is EX weight of B, here's our coordinate system. This is 15 degrees, this is the weight of B. So we're looking in the EX direction. The component is weight of B times sine of 15, and it's negative. So could say positive right here, but then when I feed that back in, it's going to be negative. Okay. Remember, mass of B is just equal to the weight of B divided by gravity. So we are in a similar place. We have this, we have this. I don't know the acceleration of B, but that's the whole point of the problem. It's okay not to know that for now. But I don't know the frictional force acting on B. But friction is equal to this equation right here in the same manner as before. So I figured out everything I can from the EX direction. Just like I did for block A, I'm now going to look in the Y direction. And just like block A had no acceleration in the EY direction, block B has no acceleration in the EY direction. To reiterate, both blocks have acceleration in the I and J, but because of the coordinate system that we defined, I can now say sum of the forces in the EY direction is equal to 0. So this fact alone is precisely why we wanted to do a coordinate transformation in the first place. Okay. So if I'm looking at this thing again, free body diagram equals kinetic diagram, and specifically in the EY direction, I see normal force of B minus the weight of B, and it's going to be, last time it was sine, so this time it's going to be cosine of 15 equals 0. The normal force minus the weight of B times cosine of 15 equals 0. So the normal force of B equals weight of B times cosine of 15. Okay. So I can now define the frictional force of B. I figured out everything I can from summing the forces in the EY direction, and now I have useful information. I come back to this stuff I had over here, and frictional force of B is now equal to the kinetic coefficient factor, which was given, times the weight of B times cosine of 15. Okay, so now I have that term, have this term now, because everything's defined in this equation. Have that, have that, have that. So the last part, solving equation 1. So it is so solving this for acceleration of B, and remember this equals weight of B over G. So you have G over weight B equals so have that, have that, have that, have that, have that, have that, and we have that. So at this point, it's just plugging into your calculator. So when you do that, you get the acceleration of B in the EX direction is equal to 1.62 feet per second squared. Any questions? So what I want to reiterate here is when I was studying for dynamics tests, I would like to develop an algorithm for solving any sort of equation. So My suggestion is I always read the problem first, pull out the givens, and the givens are going to tell you which approach you should use. So from what is given, like the coefficients of friction and stuff and like weight, it's pretty obvious that you should choose the Newton's method of solving this problem. And then a lot of times what's going to happen is you're going to sum forces in one direction. You're going to get to a point where you can't solve anything anymore, and you have to start looking in the other direction. So like in this problem, I solved all that I could in the EX direction. I couldn't go any further. I jumped over to the EY direction, got a useful equation. I took this equation, put it into where I was previously halted before, and then I was able to solve the problem. So, yeah. So there's no way I'm going to finish this next problem, but I will get started on it. But as you can see, I mean, one problem just took 40 minutes, so. So this is problem 12.19 from the suggested problems.
Thank you.
Yep, have a good one.
You too.
So, like I said, there's no way. Have a good one. There's no way I'm going to solve this problem. This one's harder. But so there is a couple hints that you should train your brain to start to realize. So I mentioned one of them before. We see the coordinate system is shifted, so coordinate transformation is probably a good idea. Also, there is a rope in this problem. So we can apply the kinematic relationships of ropes in this one, or not just for ropes, it's for particles. And lastly, one more hint, which is really big. The problem gives you the coefficients of static friction and the coefficients of kinetic friction. So the problem is indirectly asking you in the first place if this force will cause motion. The problem didn't ask for that, but you need to realize that you need to answer that first. Because it's static, it gives you this, it's a hint. It's not telling you that the blocks are moving yet. I mean, if these blocks were 1,000,000 pounds and there's only 40 newtons on them, they're not going to move. So you can't use the kinetic coefficient of friction factor. So the first thing you need to do is determine if these blocks are going to move in the first place. But I'm going to tell you that they do move, so you could ignore it. But although I don't think there will be a question on a test, at least as long as this one, because this one you're basically solving two problems. You solve the problem as if it's right about to move, but not truly moving, and then you solve it the entire way again where it is moving. So, yeah. So, you could start with coordinate transformation. I showed that directly before, so I'm not going to show it again. I'm going to show the new thing. So we have rope here, and I'm going to use that to craft an equation about my system. So what am I trying to find? Acceleration of B. So I'm going to define this point right here as XA, and then I'm going to define this next point, XB, with respect to A. So the entire length of this green chord is equal to, it's equal to 2XA, 2 because there's two of these right here, plus XB with respect to A. So now I have this equation. I'm going to take the time derivative of this equation right here, and that's going to lead me to 0 equals 2 times the velocity of block A plus the velocity of B with, yep, a good one. 2 times the velocity of block A plus the velocity of B with respect to A. The question asks for the acceleration of B, so I'm going to take time derivative again. Still, 0 equals 2 times the acceleration of block A plus the acceleration of block B with respect to block A. Okay. Then the acceleration of block A with respect, or block B with respect to block A is equal to, and this is a known, no, thank you. Yep, have a good one. This is given to you. This fact, this is true for not just our what we're doing right now. Like if I want to say the acceleration of C with respect to F, that's equal to the acceleration of C minus the acceleration of F. This is given to you on your formula sheet. So I see this term right here, and I can replace it with this term. So I'm going to do that. That's going to lead to 0 equals 2 times the acceleration of A plus the acceleration of B minus the acceleration of A. Does So simplifying this, I see, so this is 0 equals acceleration of A plus acceleration of B. Simplifying it one more time, acceleration of B equals negative acceleration of A. So although I don't have numbers yet, I just defined a very useful equation for the acceleration of B. And that is, at least half of this problem is finding the acceleration of B. So, I'm gonna stop there because that's all I can, that's like a good stopping point. The rest is much longer. Thank you all for coming. Oh, I forgot to take attendance today. If you were here, can you email me?
Okay.
So here's my email. That's my email. NA Green. And if you guys had friends who left, can you tell them to, because I don't know their names. So.